All right, let's get back into it. So the next couple of lectures are going to be on molecular spectroscopy. And spectroscopy, a whole branch of science which centers on the interaction of light with matter, typically to find out something about structure of the molecule, and so we'll highlight just some of those. Now, again, we're gonna stick with diatomics, with diatomic molecules in the gas phase. Okay, so again, they might be homonuclear diatomics or heteronuclear diatomics, and so the general picture that's gonna be pervasive here is basically two atoms bonded together. We'll call this one M1, call this one M2. There will be a center of mass. I'll call it COM, center of mass. And we'll usually center our coordinate system on that center of mass. And so there'll be a distance to mass 2, which is going to be R2. A distance to mass 1 we'll call R1. Okay, so that's the picture that we're gonna use. And so the energy of this molecule can be parsed into 4 buckets. Right, so can be parsed into 4 buckets, so to speak. And so that's going to be the electronic energy, be the vibrational energy, the rotational energy, and the translational energy. So this molecule can actually move in space. Its center of mass can move. Again, if you're talking about a bucket of say hydrogen atoms, or let's focus on the CO molecule, because actually the CO molecule is used a lot in this chapter. So if we have a bucket of CO molecules, right, these are moving with some speed in the gas phase in this bucket, and so that would be their translational energy. And so we're gonna focus on these in turn, and take a look at these energies. We're going to see how they scale. They're going to have associated quantum numbers to them, and so we'll look at them sort of one at a time. I should point out, though, that there's a lot of interaction between these buckets of energy. So again, the quantum chemistry of molecules gets quite complicated in a wonderful way, and we won't be able to get into that much. So, but we'll look at each of these in turn, and we'll start with the rotational energy. Okay, so again, the picture that emerges here for us is we'll have So it's going to be the x-axis, the y-axis. This would be the z-axis. We'll have a couple of atoms here. There's one. All right, there's two. We'll call this M1. We'll call this M2. This will be the center of mass. The distances from the center of mass then will be R1 and R2. And there's actually three what are commonly called degrees of freedom here for a diatomic, and so one can imagine that there would be rotation about the z-axis. So you can imagine that this diatomic molecule is rotating about the center of mass, about the z-axis. It can rotate about the y-axis, and believe it or not, it could even rotate about the x-axis here along the internuclear axis. And so typically people don't really address that very much because the energies, right? The energies for rotation about the internuclear axis are very large, and so they're not generally observable as is highlighted in a footnote in your text. And so we won't address it as well. So we'll look at just the 2 degrees of freedom, right? The 2 degrees. The 2 degrees of freedom about the z and y axis. So again, I want to point out that the energy is all kinetic, right? So the energy is all kinetic, and it will have an angular momentum. And the angular momentum, be it about z or y, right, is going to be then m1 v1 r1 plus m2 v2 r2. Now keep in mind now that from rotational kinematics that V1 is equal to R1 omega, V2 is equal to R2 omega, and so we can actually plug those in to here and here. The angular momentum then is going to be M1 R1 squared omega plus M2 R2 squared omega. We can factor out the omega, leaving us with this equation. And so you'll recall that for a point mass, the rotational inertia is equal to mr squared. So then this then is going to be the rotational inertia for 1, the rotational inertia for atom 2 times omega. And then that's just going to be equal to I for the entire molecule times omega. Okay? And let's just store that for a moment, and let's go and look at the rotational kinetic energy, which is going to be 1/2 m v1 squared plus 1/2 m2 V2 squared. And again, substituting in for V1 and V2, this is then going to be 1/2 M1 R1 squared omega squared plus 1/2 M2 be R2 squared omega squared. We can factor out the 1/2 and the omega squared, so this would be M1 R1 squared M2 R2 squared omega squared. And again, we recognize this as the total rotational inertia, and so then this becomes 1/2 I omega squared is equal to the rotational kinetic energy. So again, looking at L squared would be I squared omega squared, which means that we can write the rotational energy in terms of the angular momentum, and so that will be equal to L squared over 2I, and that's probably worth a box. Okay, beautiful. So let's then move to looking at this molecule as rotations about the center of mass. Now the next derivation is actually a little long, so I think what I'm going to do is I'm going to end this part here, and I will pick it up in the next section, which will give me enough time to be able to finish the discussion. Okay, very good. Thank you.